Hey guys, welcome to Algos Explained. I'm David Kim, and we are going to go over a LeetCode question. Today we're going to be looking at how to invert a binary tree, or as far as what they want in terms of inversion. And so, if you've been following my channel, you know that I do algorithm questions, and I used to do a lot on Code Wars, but I'm going to start doing more on LeetCode just because I tried the platform and I like it a lot better. In particular, I like how we can see the outline of these trees like that, and I like how easy it is to look at other people's solutions once you have a working solution. And maybe in another video I could just go over how to what my tactics are in terms of tackling hard problems. But today we're just going to go with this easy one. We have a tree, and it is defined like this over here. The tree node is just going to have a value. It's also going to have a left and a right children. And we're given that this is a binary tree, and so we know that one parent is only going to have a left and a right. It's not going to have a third child in any way. And but we don't know also that we don't know if it's going to be balanced, and we don't know if it is going to be in perfect. I want to say perfect order, but that's not the right way to say it. What I'm saying is, if you think of a heap tree or a heap, uh, it's always going to be filled from left to right, kind of. But in a binary tree, there's no guarantee of that. This 6 might be gone, and it'll still be a legit binary tree versus it wouldn't be a legitimate heap, because then the 9 would be here in a heap. But anyways, this is uh, this is kind of the input that they're giving us, and in LeetCode, they like to give us the input in this array format. But at the same time, when we deal with it in our code, we're going to have to be aware of kind of the vals and the left and rights that we can use. We're not going to be using the positions of this array in any way in terms of trying to reach those left and right nodes or the left and right children. And so this is our input, 4 being the root that we're given in the top of this function. And in the end, they want us to return something similar to that. Let's see. The only directions they have is invert a binary tree. Usually I might say that's very it's not enough directions, but this one's an easy question, and just from looking at these examples, you can actually pretty much understand what they want from us. And so the only thing happening here is the root is staying the same, and the children. So let's look at this mini tree here real quick. 4, left child 2, right child 7. All that happened here was the 7 and the 2 got flipped. So the left became the right became the left. And then now let's look at the 2 tree. This one right here, 2, 1, 3. And now that one went on over to the right side this time, but at the same time, 1 and 3 got switched to 3 and 1. In no way did 2's children get mixed up with 7's children. That did not happen. And so, and then lastly, if we look at the 7 and his children, 7, 6, 9, we know that 7 kept his children. It didn't get mixed up with 2's children, but that the 9 and the 6 switched places. It used to be 6, 9, and now it's 9, 6. And so from that, we can kind of understand, okay, what we're going to try to do is we just have to focus on making the left the right and the right the left in terms of just his children. We don't need to worry about cousins. Like say 9 is like a cousin of 3. We don't need to worry about that. We just have to focus on every single tree in terms of just its brothers and sisters and its parent. And so with that said, we can kind of know that we're gonna call invert tree. We're gonna make invert tree that function, switch the left and the right children. At the same time, we're gonna have to do it again for 2 and its children, and again for 7 and its children. So we kind of can recognize, okay, there's gonna be some recursion there because we're using the same set of functions or same functional like algorithm for each part of the tree, no matter how deep it gets. And so we can go ahead and look at that. And if you are wondering, kind of, if you have some edge cases in mind, say like maybe what do we do when there is just one child? What I like about LeetCode is that most of the time you can just run the code and kind of look down here and you'll get the expected answer. Of course, you're undefined because you didn't write anything here yet, but you'll get what's expected. And that kind of, in an interview situation, you would ask the interviewer, okay, what if we have a single node? What would we return? In this case, of course, we just return that. You might want to say, okay, in a situation where instead of just a single node, we're given a null, so like nothing like that, and the interviewer might say, okay, return null or return just like that null node or whatnot, and you have your answer here. In LeetCode, sometimes they don't let you do this, and I don't really like those questions that don't let you run the code. Sometimes they only let you submit the solution, and when they don't let you run the code, that means they don't let you create custom tests, and that's kind of annoying. But at the same time, it's all right because there are plenty here that allow us to do so. And so let's think about kind of another case you might be wondering is what if 6 wasn't there? If you delete it like that, then the 9 would be there. But if you want to, we could add a null in there to make that left child of 7 be a null. And just to go over this, how it's outlined in this array quickly. 4 has a left child of 2 and a right child of 7. Then the 2 has a right child of 1 and 3. Kind of how you would represent a heap almost, but yeah, pretty much how, like if you were looking at a heap, you would have that except for the null. But that's how the array is represented here in case you want to make some custom tests for yourself. And so let's go ahead and get to the question. If we are given a null, then we want to return a null, right? That's one of the cases that we tested out. We won't test it out again, but that could be one of our cases over here. And in terms of us using recursion, we're going to need a base case anyway. So if root is null, we can return the root. Oops, return that. And I'm not saying return null because if we were to return null, it wouldn't have the same output. Or actually, hey, it would. Okay, let's go ahead and try to send that in with our. Let's go ahead and try to send that in with submitting solution later on. I thought it wouldn't, but hey, maybe it does. So actually, yeah, of course it would, because if root equals null, then that is null. All right, and those are the hiccups that you wish you didn't have in your interviews, because they might think like, what is this guy thinking? But anyways, let's go ahead and switch our left and right. So we can just create variables. Let left equals to the root dot left, and let right equal to root dot right. And we're gonna have to flip it. So if, or not if, root dot left is equal to right, and root dot right is equal to left. And in the end, we could return root because they want us to return. So imagine that okay, wait. We missed the recursion part of it. We have to invert tree of root dot left and invert tree of root dot right. Okay, so now I feel like we got this correctly. Let's go ahead and look at yeah, let's look at how it would go in an example like this before we actually run the code, just to prove to ourselves that we understand the code we've just written. So we're given a root 4, and if it was null, then we're just going to return null. We could have returned root here, it doesn't matter because root would have been null at that point. Then we define left and right variable. We define a left and right variable. Left is the root dot left, right is the root dot right, and it might be a null, just like in that one case that we created. Here's another case that we can create real quick. Maybe the left is going to be a null, and that's going to be okay because ultimately when we throw it into our function over here, or recursion over here, it is going to return null if it's going to be null anyways. And so the left got switched to the right node, and the right got switched to the left node. And by switched, I mean it got redefined. Kind of how if you want to redefine the values of these nodes, you would go like root.left.val equals blah blah blah. But right now we're literally just redefining kind of the left and the rights. And so once we do that, it's going to go all the way down, and we're going to return the root at the very end. And so let's go ahead and see what happens here. Let's run the code with this little example first and see what happens. That is what they expected, so that's a good sign. We could, if they had this out in the array format, I would do it, but since they don't, let's go ahead and just submit this. It was simple enough, and hopefully we don't have any mistakes. Cool. And we didn't. And so that was LeetCode's invert binary tree. But let's go ahead and look at kind of how our speed compared against other people's. Right now we beat 22%, but this is not always very accurate. What I like to do is I like to do it at least 3 times just to see does that go up. And at times I have seen that percentage drastically increase. Still 22. And let's go ahead and check it again. And still 22. Okay, so maybe that's pretty accurate. But one thing that I like about LeetCode is that as long as you have a solution, you can look at other people's solution. And so you could look at that. Most people did it like this. They didn't have a separate case for root, and they just went ahead and said if root, do all the switching things that we did, and they returned the root at the very end. This person over here who got the best speed is pretty much doing the same thing. So that kind of shows right there. Or actually, well, they did it differently. He inverted the trees after he redefined them over here. And it looks like they also used one less variable than we did. And so, yeah, these people, they also inverted it before. And we're over here. Let's see if they did exactly what we did. No, not exactly what we did. We used one more variable also. But ultimately, the idea is the same. You're going to flip the left and the right, and then you're going to call the function again on the left and the right so that you can do the exact same thing on their subtrees and whatnot. And sometimes there are way too many. This might get tiny sometimes, and so sometimes it gets hard to click. You could do what I did right here. Just go to this bottom one and just drag, and you get a zoomed in version of what you want to be looking at. And you could even look at kind of what these other people were doing, taking a peek. Pretty much the same idea everybody's doing. So that's going to be it for this one. This was Invert Binary Tree from LeetCode. Thanks for watching. Remember to like, comment, and subscribe.